Good afternoon, students. I am Nipun Ahuja, Assistant Professor in MAE department. Um, Today, I will be taking your another class on engineering mechanics. I am starting new unit, Unit 4. The topics which I will present today, I will discuss about rigid bodies. What are the types of motions in rigid bodies, absolute and relative velocity, and absolute and relative acceleration. These certain topics I will discuss. They all are theoretical based, and numericals I will do in next presentation. So let's start. As I already discussed, that topics I am going to discuss are rigid bodies, types of motion, rigid bodies, rotation we will discuss, linear and angular velocity and acceleration we will discuss, and we will discuss on general plane motion, and then we will discuss absolute and relative velocity in plane motion. So let's start. Let's start doing. Let's start. Go ahead. Right. Um, First of all, let's discuss what is rigid body. As we know, basically, rigid body is a body. Uh, if we try to put different forces on the rigid body, it does not change its shape. It does not get deformed, and that is why it is known as rigid body. Right. Now, let's discuss. There are different types of motion. Well, first motion is a translation motion. In this motion, basically, suppose there is a body, this body, and you um, draw an imaginary line, this line, and if you um, if you move this body from this place to another place and let this imaginary line stays parallel, right? Then it is known as translation motion. But this translation motion can be in two forms: rectilinear translation as well as curvilinear translation. As you can see, in this case, this line and this line parallel, and also in this case and this case, these two lines are parallel. But the path being followed by this body to reach to this position, here it is linear path, so it is known as rectilinear translation. And if it and for this body to reach from here to here, if it goes through curvilinear path, then it is known as curvilinear translation. So basically, translation motion is of two types. One is rectilinear translation, another is curvilinear translation. And basically, translation is a movement of one body to other body, and the imaginary line in that body remains parallel in this case as well as in this case, right? So let's go ahead. Another type of motion is rotation. As you can see in this case, this body takes a rotation uh, from here to here, and here the center is C, which is inside the body. And in this case, the body rotates from this position to this position, and whereas the center is outside the body, right? So these are the two cases of rotation motion. And there is another motion which is known as general plane motion, when uh, when the motion is actually neither a translation or rotation but mixture of both of them, that is known as general plane motion. So basically there are three types of motion: one is translation, second is rotation, and third is general plane motion. Now let's go ahead. First of all, we will discuss rotation, right? Now, let us take an example. There is a body. This is a rigid body, and this rotates from here to here. I mean, first the body was lying in horizontally, and it actually rotated to theta angle. And this is an imaginary line. OP line is an imaginary line. So, as we know that the angle of rotation is theta, so definitely angular velocity will be d theta by dt, which this we know. And also we know that angular velocity, if we know the revolution per minute, then we know that omega equal to 2 pi n by 60 radian per second. So basically, angular velocity can be defined two ways: d theta by dt, that is change in theta with respect to time, and omega, which is also equal to 2 pi n by 60. So we know angular velocity, and now we can find out angular acceleration. If we again differentiate this thing, that is omega, we get angular acceleration, that is denoted by alpha. and angular velocity denoted by omega, right? So we get d square d theta upon dt square, right? So this is radian per second square. The unit of this is radian per second square. So in rotation, basically we understand angular velocity and as well as angular acceleration. Now let's go ahead. Now, now let's discuss some more on rotation, something more on rotation. There are two types of rotation. One is uniform rotation and another is uniformly accelerated rotation. This is similar to the uniform motion and uniformly accelerated motion when the motion was actually not rotational based but a linear motion was there. So as we know that in uniform motion velocity is constant and acceleration is zero. In this case uniform rotation the angular velocity is constant and angular acceleration is zero. And for the uniformly accelerated rotation, the angular acceleration is constant. So do remember these two cases because if in numerical you find that this word uniform rotation, so you should understand when the uniform rotation is given, you have to use angular velocity constant and angular acceleration zero. And if it is given uniformly accelerated rotation, at that time acceleration is not zero, angular acceleration is not zero, but it is constant, right? So these two things you remember. Now there are also equation of motion for angular motions also, right? For rotational motion, I would rather say. As we know for rectilinear motion, we know v equal to u plus at. Similarly, for angular motion, we have omega equal to omega naught plus alpha t, where omega is the final angular velocity, omega naught is the initial angular velocity, alpha is angular acceleration. And here s equal to ut plus 1 by 2 at square. Here we have theta equal to omega naught t plus 1 by 2 alpha t square, where theta is the angle of rotation, omega naught is angular velocity, initial angular velocity, alpha is angular acceleration, t is the time. Another formula v square equal to u square plus 2as. So here the formula is omega square equal to omega naught square plus 2 alpha theta. So do remember these three formulas also as you have remembered these three formulas, because for angular motion or rotational motion we have to use these three formulas for our numericals, right? Now let's go ahead. Now uh, let's discuss that linear and angular velocity and linear and angular acceleration. Let us say that let us take a case. There is a rigid body which rotates from this position, horizontal position, to this position at angle theta from horizontal, right? So this is theta angle. So let us suppose when this theta angle rotation is there, then at that time the linear velocity is v, and tangential acceleration is at and normal acceleration is an, right? So and this is angular acceleration, this is alpha. So let us find a relationship between the linear and angular velocity and linear and angular acceleration, right? So as we know that the linear distance is equal to basically r, that this radius, and this theta, the angle of rotation. So we know s equal to r theta, so we can find out ds upon dt, which is equal to r d theta by dt, and ds by dt we know v, d theta by dt we know omega. So we get v equal to r omega. So basically, linear velocity is equal to product of radius into angular velocity, right? So this is the first case you should remember. Second thing you should remember, there are two components of acceleration, of linear acceleration basically. One is tangential and normal, and another is normal component, as already shown here. This is a tangential component, this is a normal component, right? So we know tangential acceleration is equal to dv upon dt, and normal acceleration is equal to v square upon r. These formulas we already know, we have done in our basic classes, in junior classes. So if you do not know, do remember these two formulas. The tangential acceleration is equal to dv upon dt, and a normal acceleration is equal to v square by r, right? And we know v equal to r omega and alpha equal to d omega by dt, which we have already explained in last section. So when we put this, we get at equal to r d omega dt, which is equal to basically alpha into r. D omega is d omega by dt is alpha, and r is here. So basically tangential acceleration is equal to alpha into r, right? This r is wrongly written. This is actually alpha into r, right? And another formula, an equal to r omega v square by r, we have said. So when we put for v equal to r omega, we get an equal to r omega square. So remember these three formula: one v equal to r omega, second at equal to alpha into r, and normal acceleration equal to r omega square. So these three formulas are very important for our future for our numericals, right? Now let's go ahead. Now let's discuss, as we have discussed rotation. Now we will discuss plane motion also. The examples of plane motion is like, suppose there is a rotation of a cylinder. Now you can see when the rotation is, cylinder on a ground floor. At that time, rotation is also happening as well as translation is also happening. So basically, this is a general plane motion. Another example is like suppose some spherical thing is moving from one position to another position, then this ball is actually moving translatory also as well as rotation also. So it is a mixture of both. So it is a plane motion. Another example here is now this thing is connected to this thing, right? And when this goes up, this will come to this position. So basically, this thing is rotating also as well as this translatory motion is also there. So this is also a plane motion. These are some of the examples of plane motion. Now let's go ahead. Now let's do some more discussion on plane motion. If you see this thing, this is at initial position and finally it reaches to this position. So basically this is a plane motion. To describe this, we will see this thing, that first of all this will move to this position, that is a translate, there is a transition there, and then finally here to here it gets rotated. So there is a rotation also about the end A. So basically this motion from this to this there is an involvement of translation as well as rotation both. So this is also a plane motion. Another example, you can see that suppose this ball is here and it reaches to this position, and this basically uh, A1B reaches to this position A2 B2, right? So again there is involvement of translation as well as rotation both. First the ball moves from here to here. This A1 B1 and A2 B2 are parallel. So this is a translation, and then it rotates from here to here. So basically, if we break this plane motion into these two parts, translation and rotation, so basically we can see that there is involvement of translation as well as rotation both. So this is also a plane motion, right? So now let's go ahead. Now there is an absolute and relative velocity also. In plane motion, there is a derivation related to this. So how to do this? Suppose this is a body, right? And this moves from here to here. Actually, this thing moves A1 B1 to A2 B2, right? And this is A2 B2 dash is a basically translatory motion, right? So if we see that this whole distance B1 to B2, this distance is suppose RB delta RB, and B1 to B1 dash distance is delta RA dash, and B1, and if we B1 dash move from here to here, then this is delta R B by A, right? So we can say that this delta RB is actually the sum of delta RA plus delta RB B upon A, where this delta RB is total displacement of A1 B1 of this from here to here, and this is a this delta R is basically translation of A1 uh, from here to here, this translation, and finally this delta RB by is actually displacement due to rotation of the end B1 about A1, right? So uh, so mathematically we can put it like this. Now if we differentiate it, we get VB equal to VA plus VB upon A, where VB is the absolute velocity of the point V1, right? VA is the absolute velocity of the point A1, right? Uh, and VB upon A is a relative velocity. Uh, uh, this from here to here. So this is a relative velocity. So basically, this VB is the sum of absolute velocity of VA and relative velocity of VB upon VB of VA of VB with respect to A, right? So finally, we can find a relationship of absolute velocity as well as relative velocity in general plane motion. So this formula always remember, this formula you also remember, and this diagram you remember to understand absolute and relative velocity, right? Let's go ahead. Now if we continue this thing ahead, we can also find the same relationship for acceleration, right? So if we see that if you can see that this this uh, uh, this this body is moving from A with velocity at the point A is moving with velocity VA, and P is velocity with respect to A, that the relative velocity of P with respect to A is Vp upon A. Then Vp will be equal to Va plus Vp upon A. If we differentiate this thing, we get Ap equal to Aa plus Ap upon A, where this Ap is the acceleration of any point P in the rigid body, and this A is basically vector sum of the acceleration of the pole A and the relative acceleration of point P with respect to the pole A. So basically AP is equal to AA plus AP by AA. So this is the total velocity of P, and this is the AA is the absolute velocity of A, and AP upon A is the relative velocity of P with respect to A. So basically we can again find the relationship of absolute acceleration and relative acceleration, right? So now let's go ahead. Okay, this is these topics actually I wanted to discuss with you on today's class. In next class, we will do certain numericals uh, to related to the topics which I had just discussed. Another topic which I will discuss is instantaneous center, and then we will do some numericals on instantaneous center also. This instantaneous center is also very important topic for Unit 4, right? So now we will go ahead in next presentation. This is enough for today. Thank you. Thanks a lot.